Okay, good. We're recording now, and we had our exam last week, and then Monday was a holiday. Today is Wednesday, the 13th of November, and we're going to continue the chapter on work, chapter 6. Okay, so let's update this thing here. That should be work 3, and the first hour. UCM, here is gonna be UCM, and then I'm gonna do the lab on uniform circular motion. Here we should have chapter 6. Let me, just update it. That's going to be our version number 7 for the syllabus. I uploaded the correction of lab report number 4. And you can take a look at your Google, the folder, right? A group folder in the Google Drive. Now, look here, the exam, third exam is very close, right? I'm thinking about postpone it to the other week. Otherwise, we won't have much time to cover the material. Let's do that. Let's postpone this exam here instead of, a week from now. A week from now, right? It's too early. A week from now. Let's say 2 weeks from now. Let's see. I will fix it here. We're almost over, right? Let's see here. Yeah, okay, so this guy goes here. This one goes here. No, this one. No, this thing is supposed to be, okay, so this thing is supposed to be a lab. Okay, so that's the problem. This one is supposed to be a lab number 7, right? The exam would be the other week. UCM2, lab 7, UCM2, exam, and we should expect, to have chapter, let's see, let's estimate us being chapter 8 and 9. I don't think we'll be able to cover that, but and 13, yeah, or 11. There should be 12 here. Let's see if we can make it. And oh no, 12 is not here. That's going to be the exam here. Red, but like that. Okay, so the exam now is the 27. I will adjust this one. Uniform circular motion 1, uniform circular motion 2. Okay, and we're gonna have only 7 labs. So I can use this Wednesday here for a lecture. That's this chapter is important here. I don't want to miss this one. Very important chapter. Oh, chapter final exam. Wow. So let's see how many weeks is left. 1, 2, 3, 4 weeks left until the final exam. Okay. Any questions? Let's see, what are going to be the chapters here? Chapter exam 2. Okay, gotta put chapter 4 here for now. Let's put chapter 4 through 8, and I'll update you whether it's going to be those chapters. 7, version number 7 for the syllabus. Okay, so let's go to our, okay, here you go. 1. Exam 3 set for 27th, for November 27th. Okay. 2. I corrected the reports for lab 4 and uploaded to your group folder. Okay, and let's put this one like that. Yeah, okay, good. All those numbers here correspond to the section number, okay? And let's take a look at chapter. Which chapter are you looking at? Here you go, chapter number 6, work and energy. Chapter 6, work and energy. Okay? And let's see what we did. I was talking about conservative and non-conservative forces, right? Okay, last time I was talking about conservative and non-conservative forces. Conservative forces. You have to know the difference between them. It's very important that you know the difference between them, because the difference between them gives rise to what we call the potential energy. Okay? You must understand their difference for a very good reason. For a very good reason. Huh? Because of the potential energy. Potential energy, okay? And is another, if so now you have 2 types of energy. 2 types of energy so far. Kinetic energy, which is energy due to speed, okay? And now I will introduce you to the idea of potential energy. Energy, which is energy due to position, okay? To position. 2 different types of energy. The definition of potential energy, the definition of potential energy depends on the concept of conservative force. Conservative forces. Okay? Okay. There is one more thing. Okay, potential energy is energy associated with the work of conservative forces. Okay? That's why you have to understand the idea of conservative forces. Okay? Since, on the other hand, non-conservative forces has no potential energy associated with them. That's the little secret here. On the other hand, comma. seems to be something, the idea of conservative and non-conservative forces seems to be something like far out, unnecessary, but it's very necessary for you to understand the idea of potential energy. Okay? You must. And remember, recall it, right? Just to remind you, right? Conservative force is a force whose work does not depend on the path. Conservative force is a force, a conservative force. Let's see. Let's write it this way. It's work does not depend on the path taking from one point to another one. Another way to define conservative force. Another way to define conservative force. The work done by a conservative force along a closed path is equal to 0. Okay? That's what conservative force is. Non-conservative force is the opposite, right? Non-conservative force is the opposite of the above. Okay? Examples of conservative forces. Well, one, the weight. Whether it is the weight nearby the surface of the Earth. Okay, the weight nearby the surface of the Earth is mg, right? The weight or the gravitational force of a given mass, right? And the equation for this order of a given mass according to the universal law of gravity. Okay, and that equation that you must memorize. The force between two masses. Here you go. I'm going to write down like that. F sub G. Oh, F sub G. Okay, G. And I'm going to put M1. I'll use like that. Now let's look. Big M. Small m. R square. And everything else can be erased. This force is conservative too. So there are very few conservative forces, okay? A third one that you already know, right, is the elastic force. Elastic force is also conservative. Put that here. I have to trick Word to do something like that, otherwise it's not gonna obey me. Elastic force. What the elastic force is? Like that. Keep go. I hate when he does that. Yeah. Put it here. Elastic force. And I'm gonna even put that in vectorial format, make it more generic, okay? We must have a negative G here. And we are going to have also a hat, like that. Vectorial format. Elastic force. There are more, but there are more conservative forces, but we are going to stick by those three, okay? Here you go, elastic force. Those are the ones that you have to memorize. Everything else is gonna be, unless I tell you otherwise. Here you go. Unless I tell you otherwise, all the remaining forces will be non-conservative. So we have this complicated definition of conservative and non-conservative forces. And here we have the examples of conservative forces. I think it's easier to memorize which one are conservative, which one are not conservative, okay? All the remaining forces will be non-conservative. Let me get another document here. Notice that we're already on page 134. Huh? Okay, so because so all those three forces, so all these three, all of these three forces, they have a potential energy associated with them, whereas the force of friction, okay, tension, etc., do not have any potential energy. Okay? So unless I tell you otherwise, all the remaining forces will be non-conservative. Keep that in mind. But more important than that, okay, more important than that is this concept right here, this result that we got here. Okay, this result right here, the work kinetic energy theorem, explain the whole chapter, explain everything else. Once you understand the work kinetic energy, once you understand and memorize, first you memorize and then you understand, right? Once you memorize the work kinetic energy theorem, you can do 90% of the work here in this chapter. You can understand. I have 90% of the work here of this chapter. Okay? The only thing that is not going to be covered by the work kinetic energy theorem is going to be this section here on power. Everything else, can be explained in terms of the work kinetic energy theorem. So let's go back to the work kinetic energy theorem because this is very important. Okay? If you haven't memorized that yet, you must memorize it. And it's not that difficult. Going back to the work kinetic energy theorem, going back to the work kinetic energy theorem. Okay? I'm going to write that down here. The work kinetic energy theorem is going to be what? Is the work done by the net force. And the work done by the net force is what? The final kinetic energy minus the initial kinetic energy. Like that. Can you remember that? You can even write like that, a delta KE, right? Delta KE. And sometimes I put a parenthesis here. Okay, if you memorize this simple result, you have 90% of the chapter covered. 90% of the chapter covered. And now that and let's not forget, right? Work done by the net force, remember, now we have this new definition of types of forces, okay? You can write down the work done by the net force can be written, right, as the work done by the contact forces, right, plus the work done by the non-contact forces. Non-contact forces, right? That was the first definition of the types of forces that we saw before, right? But then we redefine the forces, the types of force that we have out there. Not only we have contact and non-contact forces, we also have what? Conservative and non-conservative forces, right? And this work of the net force can be broken down as a work done by conservative force and work done by non-conservative forces. That's how we can write the work kinetic energy theorem. Am I going now to write down in terms of conservative forces? So we don't need this thing here that I put it, and just we define that in terms of conservative and non-conservative forces. That's the work kinetic energy theorem. Let me erase that. I'm going to erase that. Final kinetic energy minus initial kinetic energy. Okay? I told you that conservative forces have a potential energy associated with them. Okay? Potential energy associated with them. And the way we define the potential energy, okay, and the way we define not just define potential energy, not just potential energy, define not just potential energy, but difference in potential energy is in terms of the work done by the conservative force. Okay? Conservative force. The way we define is a very convenient way to memorize this equation that you see right in here. Okay? Remember, it's just a definition. Okay? But it's a definition that's very useful. It's very useful. So to memorize. So two different ways, right, of memorizing this equation. You're going to see that this work kinetic energy theorem is going to be reduced to a more intuitive equation just by defining the potential energy, okay? Just by defining the potential energy in a proper way, okay? The above equation, the work kinetic energy theorem takes a format that is far more intuitive and easier to memorize, okay? So here you go. How do we define the potential energy difference? We define the potential energy difference in the following way, okay? The work done by the conservative force is going to be minus, very important, the sign here, the difference in potential energy. Okay, that's how we define the potential energy difference in terms of the work done by the conservative force. If you want to keep on using this equation, that's fine with me. Okay, that's fine with me. But when we define the potential energy difference in this way, what's going to happen to this equation here is going to become more intuitive. We're gonna have a more intuitive format. The potential energy difference is just like the kinetic energy difference, right? Is going to be given by the final potential energy minus the initial potential energy, like that. Okay? And now let's substitute this definition right here. Okay? So you can appreciate the intuitive format, the more intuitive format that you're gonna get. I'm going to expand that, okay? Because we have a negative sign in there, the final potential energy is going to become negative, right? And the initial potential energy is gonna have a positive sign. And here you go, I'm gonna get this guy here, substitute that right in here, right? And what we're gonna get? We're gonna get a more intuitive format of this work kinetic energy theorem. Look what's gonna happen, this format. Whatever is final, right? Final energy is gonna go to the right side of the equation. Whatever is initial energy, it goes to the left side of the equation. We change the signal, the sign. And I prefer to put this guy here, commute it right in here. All right? So now, look what we have. We have potential energy plus kinetic energy. Let me put this potential energy here, commute also the potential energy with the kinetic energy. See, we have potential and initial potential energy plus initial kinetic energy, plus another term, which is the work done by the non-conservative force, is going to be equal to the final potential energy plus the final kinetic energy. Okay? Most of the time, let's see. Not most of the time, in certain cases, not in certain cases, in many cases, the work done by the non-conservative force is going to be zero. In other ways, there will be no, in other words, the work done by non-conservative forces will be equal to zero, okay? So that's a special case. Let us look at this special case. Let us look at this special case, okay? Okay, if is equal to zero, comma, then the work kinetic energy theorem becomes right in here, becomes something like that. Okay? Remember when I told you that now we have a more intuitive format for the work kinetic energy theorem? We're going to have initial potential energy plus initial kinetic energy is going to be equal to final potential energy plus final kinetic energy. Can you memorize that easily? Okay. Okay, the terms in the left and right side of the above equation are also referred as mechanical and the mechanical energy of the system as the mechanical energy of the system. And we just abbreviate that by the letter E. Okay? So this equation can now be rewritten as being, here you go, the initial mechanical energy must be equal to the final mechanical energy. And that is the very concept of conservation of energy. Okay, conservation of energy. And conservation, where conservation has a different meaning than the one we are used to, right? We are used when we talk about conservation, right? Here you go. Conservation of energy, right? We usually associate this term to energy savings, right? Energy savings. That's what we usually think. But in this term, in this type of situation, conservation of energy, however, in this type of situation, conservation of energy means something else. Means something else. It means whatever you have at the beginning is equal to whatever you have at the end. That's what the very meaning of conservation here in this in this context. Okay, in this context, instead of type of situation, in this context, right? Conservation of energy means something else. It means whatever energy you have at the beginning, is equal to whatever you have at the end. And the idea of conservation applies not just to energy, it applies to other concepts, okay? You can have conservation of energy, okay? Initial energy, which means initial energy is equal to final energy. But you can also apply this idea, this concept of conservation to other parameters as well too. Okay? If you have, right? If you have conservation of energy, what does it mean? It means that energy at the beginning is equal to energy at the end. But you can also apply this idea, this concept of conservation, not just to energy. You can have, let's say, conservation of velocity, okay? Yeah, you can do that. Initial velocity, what does it mean? It means that initial velocity is equal to final velocity, okay? You can also, let's say, if the net force is constant, right, you're going to have conservation of acceleration too, right? Initial acceleration will be equal to final acceleration. And then, and so on, and so on. Later on, you're going to see other things that conserve, not just energy, okay? You do have conservation of the velocity whenever the net force is equal to 0. Okay? You do have conservation of acceleration whenever the net force is constant. The net vectorial force is constant. Okay? And now the little trick here is to find out what's the equation. Okay? Now the trick here is to find out what is the equation for the potential energy of the weight. Don't forget, we have two equations for the potential for the weight, right? Both nearby the Earth's surface and far away from it. And the elastic force. Okay, that's the little trick here. Okay, and I'm going to introduce you to this equation. Okay, let's not forget. So let's look at potential examples of potential energy, right? Here you go. And you're going to start from the beginning, from the very definition, okay? The easiest one is going to be the weight at the surface of the Earth, okay? F equal to mg. If let me get the illustrations here that we're going to need. Let's see here. That's going to be for the, let's see here. Okay, right here. Here you go. Here the weight, right? And we are going. I'm gonna give you the final result. But remember, it all comes from here. Okay, the potential energy difference is given in terms of the work done by the weight. So here you go. We use something similar to that one here. Okay, so here you go. I'm gonna use this one, and we're going to move a mass from one place to another one. Okay, instead of net force, what I'm going to do here, I'm going to get the work done by the weight from, let's say, I'll call that point A to point B. Okay. And point B. So let's say I'm moving this guy throughout any path, right? We don't have to worry about the type of path that you're moving this guy because, you know, the force is a conservative one, right? So here you go. Weight here, weight there. You already know that the work done by a conservative force doesn't depend on the weight. It depends only on the final points. Okay? And the way we do that is just Oh no, here you go. We have this delta R right here. See that? We have this delta R right here. Let's put delta R in there. Delta R. Displacement vector. Work done by a force depends on the displacement, right? Not on the position of the force. So here you go. I'm going to put in different color. So you know those are different vectors. Okay? And let's not forget what accounts for the work done by the force is just the component of the force that parallel to the component of the displacement, right? This displacement that you have right here has two components. One along the vertical direction and another one along the horizontal direction. This delta R is going to come right down here, and I'm going to put that in blue. Like that. Let me move it, shrink it a little bit, right? So what do you have here? Okay, if here is delta R, point A, we're going to put, bring it down, okay. Point A. If this one here is delta R, what you see right here is going to be delta X, okay? And if this one here is delta X, this other one here is going to be delta what? Y, right? See that? Y naught minus Y final. See? Let's see if I have it in horizontal. Make sure everything is, oh yeah, see, it's not completely in the horizontal. That's why those grids are useful. Find out if I'm doing everything in the right way. Right in here. Let me take out the grids because the grids, you know. But, you know, so what we're going to have, the work done by the weight in this case is going to be what? Look, the weight is down and the displacement is up, right? There is no weight along the x direction. Consequently, delta x does not cooperate towards the final work done by the weight, right? So here you go. Work done by the weight. Let's put here from A to B, right? Work done by the weight from A to B. And I'm going to copy that so you can have a good reference. Snipping tool right in here. Okay. I'm gonna copy and paste right here. Refer to figure below. Okay. Oh, wait a minute. Oh yeah, I forgot to erase this one, right? We don't need that. We don't need that. And even better, let's see. Red, right? Let's put this one red. Let it make it more user friendly, right? You want to make it into different colors. Let's see, this one is gonna be my green color. Green color. I'll keep this one blue. This one, I'm gonna make it, let's see, this color here. And then, and this one, which color is left here? Maybe brown. Yeah, brown is a good color. Yeah, here you go. And point A, and let's see, RF. Point B is gonna be green. Here you go. Point B, like that. Another student coming in. Let's get this picture again. Okay, now we paste into our notes, this one here. Now the figure is supposed to be more friendly, more user-friendly, right? Easier to understand. Okay. From this figure, we note that the work done by the weight is from A to B, right? By the way, from A to B is gonna be what? It's gonna be mg with a minus sign times delta y. That's the very definition of the work done, of work, right? Where delta y is what? Delta y is going to be final y minus initial y. And we don't have y here anymore. Recall that the definition of potential energy is minus its work, right? Potential energy difference, okay? It's minus the work of its force, minus the work of its force, or, right? Potential energy difference is equal to minus the work done by the force. I have everything already here, right? Right? Here you go. Minus the work done by the weight. See where we are getting here? Here you go. And then what we get? Minus sign cancels this minus sign, right? And becomes what? mg delta y. Okay? And I'm going to put this guy between parentheses here as well. So here you go. But don't forget, that's the potential energy of the weight of mg. This one we can do the mass because it's the simplest of all cases. Okay. The other ones, no, they're not. The other ones are not that easy. Okay. The next one. Okay. So here you go. Potential energy difference. It's gonna be this one here. Okay. mg delta y. Now, work done by the gravitational force, right? According to the law of universal gravitation. That you have to memorize. We cannot derive it here. Okay, it's going to be what? Gravitational force. I don't. Here you go. I'm gonna put just big G here. All right. This is gonna be, big G, big M divided by R. Okay, so let's see the potential energy of the planet Earth. Right? It's gonna be big G times the mass of the planet divided by the distance from its center. You go. Where R is the distance from the center of the planet. Okay. And we have another one. The other one we can do. We have done. We can do the calculation, but then we have to rely for the elastic force. The potential energy is given by, okay, potential energy, here we go. And we did already the work done by the elastic energy, by the elastic force. We did that before, remember that? It's gonna be half kx squared, okay? We got a minus there before, right? But we got a minus there before because we're calculating the work done by that force. The work done by this force has a minus. The work done by this force has a minus sign. Okay? So we have those three important potential energy equation for the potential energy difference. We can calculate that. We calculate that before by doing the work done. And this one we cannot calculate here because it requires calculus. Okay? For the above equation can only be derived using calculus, differential calculus. Okay. This one, we can do that. This result can be obtained by calculating the area below the curve of the equation of the elastic force, right? Like that. So 247 now. Any questions about that? We'll be using all those equations to solve problems of physics that use conservation of energy. Okay. So here we go. I wanna get my spreadsheet here. No, it's not what I want. This one is that I want. Attendance. Lecture, yeah. Lecture is not a lecture, it's a lab. Today is the 13th. That was the exam, right? Exam 2. Exam 2, this one. Insert. Jazzy Castellano. Are you there, Jazzy? Yeah. Okay, Molly is asking me if I teach physics 2. You might be referring to physics 7, right, Molly? Yeah, okay, so yeah. This one is physics 6, right? The continuation of this course is physics 7. Yes, I am scheduled to teach physics 7 for the next semester. And if you want to continue, if you need to take physics 7, I strongly encourage you to join me next semester. Okay, so let's write that down here. Okay, I will be teaching physics announcement, right? Physics 7 next semester, spring 2025. And if you need this course, I strongly encourage you to join me. Join me next time, next semester. Okay. A little bit here of advertisement for my course. And that's a very interesting course. I think it's much more fun to teach physics 7 than 6. Okay. So going back to attendance here, he goes, Jazzy is here. What about Gabriel? Are you there, Gabriel? I don't see Gabriel Contreras here. Nohamin? I see. Thank you, Nohamin. Liliana Cortez? I don't see Liliana Cortez here. Molly is definitely here. Okay. Henry Kim, are you there, Henry? I don't see Henry here. Laurel Williams. I can see Laurel is my list. Okay, I'm gonna put a star here in your name, Laurel. Must be away from his computer. Ruth. Ruth has joined us. Thank you, Ruth. Next is Noemi Martinez. Noemi is also here, at least in my roster. Yeah, here you go. Noemi is here. Danae Miller.
Here.
Yeah, okay. Thank you, Danae. Ramon Olivares. I don't see Ramon in my roster. Let me put the one next to the other one here. Okay, better this way. Taylor. Taylor Farn.
I'm here.
Thank you, Taylor. Stephanie Ramos. I don't see Stephanie here. Yeah, Stephanie is not here. Jeremiah Reyes. Thank you, Jeremiah. Sean Rosario. Thank you, Sean. Jason Strait.
Here.
Thank you. Elena Trujillo.
Here.
Thank you, Elena. Jason Valadares. Hello, Jason. Jason V. Okay, I'm gonna put a star here under his name. Audrey Aguilar. Okay, Audrey is here. Brianna Carrillo. Thank you, Brianna. Ali Standard. I don't see Ali here. Next is gonna be Alia Zavala. Zavala is here. Okay, thank you. Let's see how many. Let's see if my numbers here matches with the number that I have in my Zoom roster. 14, 16. Let's see. Yes, it match. I want to give Jason Valadares. I want to give you opportunity for you to say you're here. I have And what about Laurel Williams? I want to give you another opportunity to say that you're here. Okay, so I didn't hear from any of them. Let's keep this way. So let's go for our break, right? Break. Oh, before we go to our break, let me just show you the schedule of classes for the next semester. Since Molly asked it, right? For, let's see, 2025. Here you go. Oh, no, that's not the one I want. Okay, I gotta go to the college website. I thought I had downloaded the schedule of class, but it's right in here. Schedule of classes, admission about calendar. Let's see, academics, schedule and catalogs, right? Winter, February, that's the spring. Okay, winter session. Let's take a look here. I didn't check. Oh, now that I remember, I didn't check that. First time I'm looking into that. Okay, so Physics 7 for the spring. They're going to change the scheduling. For some reason, they changed the schedule. I do not know why. Instead of meeting 8:40, they scheduled that for 9:40. Okay, live online. This is going to be synchronous, right? 9:40 to 12:50. 9:40 to 12:50. Yeah. Huh. Interesting. Yeah, they changed it. Hey, wait a minute. Let's see. Our schedule was 8:50 to 12 noon, right? Okay, yeah. So they put 50 minutes later, and because we're 50 minutes later, and not 1 hour later, we are finishing 10 to 1. Okay. So that, I don't know why they did that, but that's the schedule. Here's my name. Okay. And that's the course I'll be teaching next semester, okay? And I strongly encourage you to register for this course. So I see you in 15 minutes. Let's go for our break, and I'll see you in 15 minutes. That's break not too. It's 9:55, right? 9:55 a.m. to 10 a.m. I see you in 15 minutes. So we're going to, next class, we're going to do some examples so you can understand how to apply all those equations, okay? And let's just see where we are right now. Here you go, chapter 6, work and energy. I'm gonna copy and paste it right in here. Okay, this note is gonna be at the end of today's note. Here you go. Gravitational potential energy, we already covered that. Conservation of mechanical energy. Yeah, we did that. It all depends on the work kinetic energy theorem. Okay, this guy here, tells everything about this chapter. The only thing that is left is just the power and other forms of energy. But I'm not gonna cover other forms of energy. Okay, I already did an example of work kinetic energy theorem. Let me see. I already did an example of how to calculate the work done of a non-conservative force last time. Remember that? So we are left with those two other sections, and that I'm going to end next time we meet. So let's see. I'm back. Okay, Larell is here. Okay. Larell. And what about Jason Valadares? Jason, are you there?
Yes, I'm here.
Okay. 16. Someone left. I can see that someone left here. Okay, we'll catch up with this person. Now, let's see. We have group 1, group 2. Group 1 has 2 students today. Group 2 has 2 students today. Group 3 has 3 students today. Group 4 has 3 students today. Group 5 has 3. Okay, and group 6 has 3. Okay. So we're in good shape here. And let's take a look at that lab number 6. Yeah, uniform circular motion. The first part of uniform circular motion. Labs 2 and 3, 4 and 5. Let's see if we can put another lab here, 5. See if we can do lab 6 too. 4, 5, and 6. Yeah, for exam number 3, 4, 5, and 6. Okay, and the chapter that we're doing, okay, chapter on work. So definitely chapter 4 showed up in the previous exam. So far we're doing chapter 5 and 6. Let's see if we can finish chapter 7 by next week, right? And they put, I don't think we'll be able to finish chapter 8. So for now, let's keep that 5 through 7. Lab 4 through 6, right? Lab 4 through 6. That's what we have here. Uniform circle. So all those concepts that we learned in the chapter of uniform circular motion, we're going to apply to this experiment. Okay? Going back to the notes. Okay, so we have just those 2 here that are left. I'm going to concentrate on this one. There's nothing much to say here on other forms of energy. Go. Other forms of energy. Okay, here you go. That's the one. Yeah, see, almost nothing. Okay, it's just a discussion, a short discussion about, and it even mentions about relativity theory. So we're going to skip. We're going to skip this chapter. Let's put it here. Other forms of energy is skip. Skip it. But we are going to address this final chapter, this final section, next time we meet for the lecture. And let's get your spreadsheet, the spreadsheet for today's lab. Lab, raw data, 6. Oh, don't forget, right? Let me put here, I didn't put at the beginning, report for lab 5. Report for lab 5 is due. Okay, it's due now. Okay. Let's see. And let me put here 3rd exam in 2 weeks. That would be the 27th. Oh, already. Already put it here. Here you go. Don't need it. It's already here. Scheduled, right? Scheduled. And 5, 6. Okay, yeah, let's take a look at those spreadsheets. The one that we are going to let's see, number one. Here you go. That's number one here. Everything seems to be fine here. Yep. Number one, let's see, number two, group number two. This one right in here. Yep. Group number three. Yep, that's good. Group number four. That's the one. Yep. Five. I'm just checking if there is no, if everything is supposed to be in the way it is. I want them to be okay. And I'm going to emphasize today about this G, okay? I'll talk to you about that very soon. I'm gonna put everything in red. Let's see, next. Five, yeah, six. There should be, oh, yeah, this guy doesn't belong here. Okay. And let me upload your spreadsheets to your group folder. Group number one, spreadsheet is there. Group number two, spreadsheet is there. Group number three, spreadsheet is there. Group number four, oops, ay, 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 ay. Group number four, do we have it here? Yeah. Group number five. And finally, group number six. Go ahead, download your spreadsheet while I check the other files here. Download the spreadsheet for lab 6, your hard drive. That seems to be good. That seems to be good. That's good. And 12. Clear. Needs. Okay. Yeah, 12. I'm gonna get chapter 5 too. Okay. Skip. So far, the material for material. So material for exam 3 so far. Material for exam 3 so far. Okay. That's chapter 5. Chapter 6 plus labs 4, 5, and 6, right? Yeah, 4, 5, and 6. Important to go. Important. Mr. Very good. To join me next semester, okay? Yes. And I have notes for chapter 6, for lab 6. Chapter 6. Lab 5. Third. Go. That's the notes for lab 6. Yeah, there's a high quality video that I made about this experiment, which I posted in my YouTube channel, okay? We're gonna get there, but before I get there, here you go. The idea here is to verify Newton's second law of motion for an object with variable mass and constant, not for an object with variable mass. Let's see. Verify Newton's second law of motion for objects of different masses and undergoing different masses and same radius undergoing uniform circular motion, like that. That's the idea. So let's see if Newton's law of motion also applied to uniform circular motion. Okay, that's the idea here. In other words, we'll find out. We'll demonstrate that Newton's second law also applies to objects undergoing uniform circular motion. In the last experiment, demonstrated that the second law applies to an accelerated object moving in one dimension. Okay? An object uniformly accelerated, right? Uniformly accelerated, moving on dimension. And now we are going to show that Newton's second law also applies to circular motion. That's how powerful this law is. So this law is so powerful that people, when they launch objects to the in orbit of the Earth or past the orbit of the Earth to other planets, they are always using Newton's second law of motion. Okay, when they are plotting the path of those satellites, like the Voyager satellite, the Cassini satellite, and others that are investigating Jupiter, Saturn, and the other planets, they always use Newton's second law of motion. And they're very successful at that, with minor corrections throughout the travel, the interplanetary travel. So now in this experiment, we have two parts here. Okay, first we'll measure the period of an object undergoing uniform circular motion of a mass, okay? Of a mass undergoing uniform circular motion. After that, then we will measure the force required to keep this mass rotating at a given radius. That's what we're going to do. The equipment that we are going to use is the Senkos centripetal force apparatus. Let me show you how it looks like. Let's go there, here, Senkos. Centripetal force apparatus. Let's see. Okay, right in here. That's how it looks like. One of the larger. That's too complicated. Let's see. Let's see. I like that other one before. Here you go. Maybe this one. Yeah. No, no, not this one. Yeah. Let's see this one. Oh my goodness. No. Let's look for a better picture, right? I like this one. Let's see. Okay, yeah, it's this one here that we must be concerned. But I want a simpler picture. So let me show you that. This one. Can I download it? Yeah. Save image. I want to. That's not a very good quality. But the way we do this experiment, the first part, we remove this hanging mass that you see right in here. Okay, in the first part, all we do, we're going to use this set that you see right in here, okay, and put this mass here to rotate. That's the idea. And keep its radius constant. That's how we do it. And we time how long it takes to complete a total of, let's see, 20 rotations. Okay. But let's get the video that's in my. It's a high quality video. I'm very proud of that video that I made. I really enjoy doing that. It was lots of work, but I enjoy it. I had a grant at the time when I did that video. I made a total of 4 videos of physics experiment, but I posted only one because I consider that here you go. That's the one here. Let's see. Can I gotta blow it up. Okay.
Centrifugal force experiment. Constant.
Here you go.
Centrifugal force experiment. Constant radius and variable mass. In this experiment, you will verify Newton's second law for an object undergoing uniform circular motion. You will change its mass while keeping it.
Do you recognize this setup here, right? Very similar to that picture, right? You have the mass hanging, attached to a spring. The radius of motion is this one, is this distance that you see. And on the top of that, you also have this hanging mass passing through this pulley. And that would be the second part of the experiment. We want to at this very moment, we want to concentrate on the first part of the experiment. Let's go there.
Its radius of rotation constant. This experiment has 2 parts. In the first part, you will measure the period of a rotating mass. In the second part, you will determine the force required to keep the mass under uniform circular motion. Its most important element is its low friction rotating shaft.
That's how the Senko's apparatus is put together. You have this rotating shaft that has a very low friction here at the bottom. Okay, it's made up of this rotating shaft.
You will insert a crossbar near the top of the rotating shaft to firmly secure
a crossbar.
The bar. Its beveled regions must face upwards. Using the locking bolt, lock the bar along the longest of these regions. The crossbar has a string from which you will suspend a rotating mass. A rotating mass is provided. This rotating mass is a bomb. Measure its mass with a scale.
Okay, so that's the first data that we're going to get here. The mass of the bob, right? Going to one of the spreadsheets. Let's take a look here. A spreadsheet. I'll get this one. Okay, that's the one. Yeah. So here you go. The mass of the bob goes right in here in kilograms. Okay. I expect that you have your spreadsheet open right now. And let's see here. Crossbar Tenko centripetal force apparatus, crossbar with beveled regions, locking screw, locking bolt, right? Locking bolt is better. String, the bob. We are going to use a scale, the same scale we have been using that has a resolution of 100 of a gram, or 1, 2, 3, 4, 5 decimal places in the kilogram unit. And we have that indicator rod already. We already, got our first raw data. Don't forget the G that you see here. I'm going to emphasize that because it is assumed to have infinite number of significant figures, okay? Write that down. The G the G in the table below is assumed to have infinite number of significant figures. So don't forget when you start to look at the right number of significant figures here in your table. So this guy is going to be our first raw data. And now
using the provided spreadsheet, log this mass with the right number of significant figures. Suspend the bob from the string of the crossbar. At the base of the apparatus, there is an indicator rod. Slide the indicator rod until its tip coincides with the tip of the bob. Tip of the bob to the tip of the rod.
This indicator here is used as a reference to perform the experiment. Okay, if you don't have an indicator here, it's going to be very difficult to know whether this bob is undergoing uniform circular motion as a constant radius or not. That's what this indicator is all about.
Using a ruler, measure the radius of rotation of the bob.
Okay, our second piece, our second data point, raw data point. You go. The radius right here. This radius is not going to be changed, okay? Not what I want. I want the other one. Yeah, here you go. The radius right in here. Since it's constant radius, you don't have to change this value. Everything in yellow is going to be my raw data. And going back to my notes, indicator rod, ruler. Use the ruler to measure the radius of the bob. Going back, my video, here you go.
Take this measurement from the center of the rotating shaft to the tip of the mass bob. Log it in the spreadsheet. A spring is provided. Attach one end of the spring to the rotating shaft. Attach the other end of the spring to the mass bob. Pull the bob until its tip coincides with the tip of the indicator rod. Tip of the bob to the tip of the rod. While holding the bob, check if the spring is horizontal. If it is not, adjust the bob's height by either winding or unwinding the string attached to the crossbar. Remember, tip of the bob to the tip of the rod. Horizontal spring, vertical string.
You want the spring to be horizontal so you do not have any components in the vertical direction of the force that the spring is making on the bob. Okay, and you want the string in the vertical direction. Conversely, we want the string in the vertical direction for the same reason. You do not want the tension to have a component of the tension along the horizontal direction.
Lower the apparatus with the adjustable bolts until the apparatus' lower surface touches the table. Clamp the apparatus to the table with a C-clamp. Do not start the experiment until you align the bob, the rod, the spring, and the string. Also, ensure the apparatus is clamped to your table. This will prevent the apparatus from moving while you perform the experiment. Use your fingertips to rotate the shaft.
Now you put
Adjust the shaft's angular speed until the tip of the bob aligns with the tip of the rod. If the shaft rotates too slowly, the bob will pass between the indicator rod and the rotating shaft. You don't want this situation because you're going to have a component, horizontal component of the tension. And you're going to have a vertical component of the elastic force. You don't want this situation. If the shaft rotates too fast,
Likewise, okay? You want the bob exactly
will move
aligned up.
past the indicator rod. Practice this exercise a few times with the rotating shaft before you start. Once you learn how consistently align the bob with the rod, you can start the experiment. Using a timer, measure how long it takes for the bob to complete 20 revolutions. Adjust the rotating speed to align the bob with the rod. Then count down from 5, 4, 3, etc. At 0, start your timer and continue counting the revolutions until 20. Because of friction, you may need to propel the shaft with your fingertips every now and then. When you reach 20 rotations, stop the timer, read the period, and log this value into your spreadsheet.
Okay, one more raw data point here. One more raw data point. Here we go. That's 20 rotations, okay? You're going to repeat that a total of 7 times using your timer, and your timer has 2 decimal places in the second. So let me emphasize here. We didn't get to delta M yet, okay? Didn't get it, but here is raw data as well. Let's go back to our spring C clamp timers, resolution 0.01. That's it. Equipment and materials, right? And now we're going to start varying the masses of the rotating object. That's what this delta M is all about. Initially, we get the object just to rotate by itself. Let me put in the proper order, right? Instead of here you go. We did only the first one, right? So let's keep like that. We didn't add any mass to the bob. And we're going to start adding masses to the bob. Going back here.
As you count the number of rotations, ensure the tip of the bob remains aligned with the tip of the rod. Also, ensure the spring is horizontal and the string is vertical. If they are not, you may need to either increase or decrease the angular rotation. If you still can't achieve alignment, you will need to stop the experiment and realign everything. Load a 20-gram slotted mass.
Here you go. We start with 20 grams now. Now we're going to change the mass, the value of the mass. Load 20 grams to the scale and write down its value all the way down to the second decimal place in grams. Here you go. That's going to be my measurement number 2. Okay, put it to rotate again, time it, and I will have a second raw data for 20 rotations. Okay, let's take a look at the notes. 20 grams slotted mass. Right in here. And then there are other slotted masses too. I should have put more here, but let's go back here. I want to fix that as we go along. Here you go.
And determine its exact mass. Add this measurement to the bob's mass and log this result to your spreadsheet. Use the proper number of significant figures. Clamp the slotted mass to the top of the bob. The bob is a distance.
Here you go. Here my slotted mass, 20 grams slotted mass. We have a bunch of those there at LA Harbor.
With a threaded hole. Use it to safely clamp the slotted mass to the bob. Pull the bob to the left until the tip of the bob aligns with the tip of the rod. Make sure the spring is horizontal and the string is vertical. If they are not, adjust the vertical position of the bob by winding or unwinding the string. Put the shaft to rotate and determine how long it takes for the bob to complete 20 revolutions. As before, The tip of the bob must be aligned with the tip of the rod. Compare this new measurement with the first one. Repeat the 4 previous procedures for 5 different slotted masses.
There you go.
50 grams,
50 grams.
70 grams, 100 grams, 120 grams, and 150 grams.
Let's write that down. 50 grams. $20 is slotted mass. 50 grams is slotted mass. Again, we have a bunch of those there at the physics department. Now that we have one of 50 and another of 20, we can sum them up to come up with a 70 gram total mass, right? And what else? Let's rewind it a little bit. 50 grams. 70 grams is 50 plus 20.
50 grams. 100
grams we use at 100 grams slotted mass. Which other? Let's see.
Grams.
120. We combine the 100 with the 20 grams to get the 120 grams.
And 20 grams and 100.
150. We combine the 100 with the 50. So we need only 3 masses to come up with all those combinations of masses here on the top of the bob. Okay? And repeat the experiment for each of those.
50 grams. A total of 7 measurements. You will now measure the force the spring.
Okay, so the first part of the experiment is done, which is to find out the period. Here, this one is, well, here we did the slightly different. We use like 30 grams, 60, okay, 60, 90 grams. It's okay. It's 110, see that? 130 and so on, 150. It's okay. The numbers that doesn't match what's in the video, but the experiment can be done with different values of the mass. And we measure the period of rotation for 20 rotations. 1, 2, 3, 4. 4 columns with raw data. Okay, what you see right in here is the mass of the bob added to the other masses. Okay, so this one here is not raw data. This one is a result, which I'm going to put in a different color. Like that, green, okay? What you have here in this column is how long it takes for a single rotation, a period of a single rotation. So what I do? I get this value for 20 rotations and divide by 20. So that's also a result. Then we get this period of a single rotation and square it. There's a reason why we square it. And it's going to be a result as well. First part of the experiment is over. And now we are going to find out the force that the spring exerts on the mass. There's a very nice procedure to do that, very simple too. We're not going to put anything to rotate.
Applies to the bob.
There you go.
This force is equal to the centrifugal force. This part can be performed without a C-clamp, using a 1 meter long string.
Okay, string. Okay. Equipment.
Attach it to the left side of the mass bob. Pass the other end of string 2 through the pulley. Attach a mass hanger to the other end of the string.
Mass hanger.
Load.
Okay, don't forget to add there in the list of equipment, right?
Several slotted masses to the mass hanger. Load these masses until the tip of the bob aligns with tip of the rod. Also, check if the spring is horizontal and the string is vertical.
If the force is too strong, the mass is gonna move past the indicator rod, right? And you're going to have again a horizontal component for the tension that you don't want, and a vertical component for the elastic force that you do not want either. If this mass is too low, then the bob is gonna be moving to the right of the indicator. You don't want that situation either. So that's how we perform the experiment, to find out the force that the bob is subjected to. And this force here, the force applied by this set of masses, is going to be equal to the force that the spring applies to the bob during the even during the rotation. So let's see.
Using a scale, measure the net hanging
Again, scale.
mass hanger plus slotted mass. Log this measured value in your spreadsheet. Add the 20 grams slotted mass to the top of the bob and repeat the 4 previous steps. Repeat this step for the remaining slotted masses: 50, 70, 100, 120, and 150 grams.
Okay, so let's go back to our spreadsheet. Right in here, here's the hanging mass, okay? That's actual raw data. We get the masses hanging there from, hang the mass hanger, and then load the mass hanger with different slotted masses. What you see here is going to be the velocity of the mat, and there's a reason why we want the velocity. The experimental value of the force, that's mg, right? That's a result as well. The theoretical, that the value that we use, a formula to determine, and then the percentage difference between those two values, experimental and theoretical, that always going to be in green color. No, not this one. I want the other one, this one right in here. Okay. Let's take a look at our notes. Let's see if we missed anything else. Okay. That's for the first part. Determine the period of rotation. Okay, and then what comes next? Second part. Find the force applied to the bob by the spring. Okay, and then what you're going to need, that there is okay, 50-gram mass hanger. You're going to need also 1 meter long string. Yeah, here you go. Several slotted masses. Oh, I already have it here. Several slotted masses. Okay. The procedure. And we are done with this video. Let's finish it. Everything, you go.
You completed the experimental part. Now perform your data analysis and determine if your experimental results are close to the theoretical ones.
Okay, this is my business. I have a logo that I made it for it. You know, it's an illustration of the side illuminated fiber, that the technology that I invented. Okay, so that's what we have. For that, let's close that here. And let's start. Let's see. Again, it's time for our break, right? Let me just get any questions about that? Just taking time. Okay, right in here. I gotta adjust my time zone here, so I have the same time that you folks have it. Pacific time. Good. Now it's 10:58. 10:58 in Pacific time, right? So any questions? Let's go for our, if there's no questions, let's go for our break. Okay, and then I'll go through in detail of the theory of this experiment that I didn't cover yet. Break, let's see. Break 11 o'clock a.m. to 11:15 a.m., right? So I see you in 15 minutes. I am back here. Now let's take a look at the theory behind this experiment. Okay. Since we're dealing with centripetal force, we must use the equation for centripetal acceleration, right? And here you go. The equation for the centripetal acceleration is this one that you see right here. V squared over R. What you see right here is the mass of the bob. And here's the centripetal force. We do not have V, but we do have R. And V can be written down in terms of 2 pi R and the period of rotation. That's why we calculate the period there in the spreadsheet. The R was measured with the ruler. Is squaring all of those parameters here, we get something like that. And then we simplify, right? R squared simplified with R, we get this relationship here. Rearranging the equation, we have centripetal force times T squared is equal to 4 pi R squared, 4 pi square R times M. What's changing here is this guy, don't forget. This guy is changing, here you go. And this other one is changing. Those two parameters are changing. Okay. MH here is the hanging mass. The hanging mass, okay? And G is the acceleration of gravity, of course. What else? What else can you do? Okay, let's write down M in terms of everything else. What happens is that this hanging mass that you see right here is going to be constant, okay? There's a little piece of information that's difficult to see, but because we are not changing the radius of the mass, the centripetal force doesn't change either. Okay, and so everything that you see, let's see, everything that you see right here in this term is going to be a constant. Hanging mass, the G, 4 pi square, of course, and the radius is a constant. And so what do? We plot M along the y-axis and T square along the x-axis, okay? And so that's the first thing that you need to know, to do, okay? Plot, plot, here you go. Plot M along the y-axis and T square along the x-axis. So and it's now that I'm going to go through the class and see if you got everything. The first thing that I'm gonna ask you is if you downloaded the spreadsheet. Download. Today is 11/13. Jazzy, did you download the spreadsheet? Yes, okay, good. Yeah. What about Gabrielle? Gabrielle is not here today, right? Yeah, I don't see Gabrielle. She's not here. Okay. Nuhamin, are you there? Looks like Nohamin left. Oh, what a shame. Okay, I'm gonna put it here. And Liliana Cortez. I don't see Liliana either. Molly, did you download their spreadsheet, Molly?
Yes.
Okay, I'm going to put a 0 here for Nohamin since it's no longer here. Henry didn't come today, right? Okay, what about Larell? Did you download their spreadsheet, Larell? Yeah, I think so. Well, I need more assurance than that. Lab number 6, okay, group folder number 2. Okay, I'm gonna put a Y here for you. Ruth, you download their spreadsheet. Ruth is not here either. She came and then she left. I'm going to do the following. I'm gonna put a star here. I'm gonna put a star for, okay, and Noemi. Did you download your spreadsheet, Noemi? Yes, okay. Next one. Danae. Yes, that's right, Larell. P06 LO6G2. Your group number 2. Let's make sure you're group number 2. Yeah, that's right. Danae.
Yeah, I downloaded.
Okay, thank you. Ramon is not here, right? Ramon, I don't see Ramon here. Taylor, did you download their spreadsheet?
Yeah.
Okay, Stephanie Ramos. Okay, Stephanie is not here. Next is Jeremiah. Okay, Jeremiah downloaded. Sean Rosario. You download your spreadsheet, Sean? Okay, good. Jason Strait.
Yes.
Okay, next is Elena Trujillo.
Yes.
Okay, next is Jason Valadares.
Yes.
Yeah, do you have any question?
No questions.
All right, okay, thank you. And Audrey? Download the spreadsheet? Yes, okay, good. Brianna Carrillo? Hello, Brianna. Okay, I'm gonna put a star here under Brianna's name and a star under her attendance. Next is Ali Standard. Ali didn't come today. And Alia, did you download your spreadsheet, Alia? Hello, Alia. I don't hear from Alia. Let's put a star here and a star here. And the next thing that you want to do is to plot the graph. Plot graph, right? And the graph that you're supposed to plot should be written down right in here. See that? Plot M along the y-axis and t squared in the x-axis, okay? M, okay, M and t square. Let's not forget that, go. What I have here is not M versus t squared. I will have t squared versus M. So we have to swap the axis now. Let's see if we can do that. Let's see. No, we cannot do that. Sometimes it works, sometimes it doesn't, okay? So let's try the other way, right? Select data, and then we swap I. Yeah, so it seems usually that's so annoying. Let's see if I can. No, cancel. Okay, if you have a problem plotting that's easy to fix. Okay, you can like this guy did. Okay, he created 2 columns here for t square, right? And let's not forget copy here. When you copy, You go, and then you paste it. But then you paste it, you special paste it. You don't paste the regular one because the regular one is gonna paste just the equation. Okay, you don't want to paste the equation. You want to paste the numeric value that the equation is calculating. And you do that by right click and in the paste options. Do you see 1, 2, 3 here? You are pasting only the values without the formula that I put in there. Okay? And you do the same here for the mass, which is also the equation. Copy and paste the values. That's another way of doing that, okay? There are more than one way. Sometimes some of them work, sometimes some of them do not work. One of them that I like is just to drag it back. Oh yeah, I got it. Okay, see, you just drag those two parameters. Okay, now I got it. Okay, now I put the M in the y-axis. Did you see what do you understand?
Can you do that again? Can you do that drag thing again?
Yeah, let's do that again, right? Sometimes this technique works, sometimes it doesn't work. I do not know why. You know, Bill Gates should fix this type of problem. Let's first plot it, right? Insert, scatter plot. So what you have right now is t squared in the vertical and m in the horizontal. You do not want t squared in the vertical. You want t squared in the horizontal, right? One possible way to fix that is to click those points. When you click those points, look what you get. The t squared and the m get highlighted, right? One possible way to invert that would be just to click, this rectangle here and drag to the other side, and then click this other rectangle and drag to where you want it to be. And now we have the right plot. And now we have the right plot. Okay? That's one way. The other way would be to click here, right click here, and select data, right? Select data, select series, edit, and then you swap L and I. This one sometimes works, sometimes it doesn't work. It used to work most of the time, but now for some reason, it's no longer working for me. I do not know why. As a last resort, right, you can copy those numeric values and put in a separate table right in here with the t square on the left side and the m on the right side. And then you plot from here, right? But that's the last resort. And that's what my chart is. I'm going to optimize this chart. There's too much space here, too much blank space here and here, too much here. So when you're gonna publish something like that, you don't want to publish like that. You don't want to have this big blank space here. You want to spend some of your time, fine tuning your graph, make sure it looks nice. I'm gonna put, let's try 0.3. 0.3 is still not good, right? Let's see, 0.5 is okay. Okay, so what you want here is 0.4. Yeah, 0.4 is good, at least in the horizontal direction. Let's fix in the vertical now. I would go from 0.5, 0.7, okay? 0.5 to 0.7 for my 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Why do I have so few data points here? Supposed to be 7 data points. 1, 2, 3, 4, 5, 6, 7. Strange. Okay, so it looks like I missed something. Let's start from Let me put it in a way that I can identify the numbers here. Okay, those are not necessarily the right number of significant figures. M should go from 0.4 to 0.65. Okay, so let's go from 0.4. Why 0.41? Okay, 0.41 is the other one. Okay, okay, I'm missing. I should go 0.3. Yeah, that's why we have only a few points in there. 1, 2, 3, 4, 5, 6. Now I'm supposed to have 7. Yeah, supposed to have 7. So there's one more data point missing. Let's see, where is this data point? 3, 5, 3, 8. Must be there. 1, 2, 3, 4, 5, 6. Strange. Okay, is it below 0.5? Oh, yeah, right. Let's see. T square is in the horizontal, M is in the vertical. Okay, so we should work right in here. 0.48, we want 0.45. Okay, now I have all the points. 1, 2, 3, 4, 5, 3, 4, 5, 6, 7. Yeah, I have all the points, but then I have to make a better graph, 0.35. Okay, now I have a good graph. I may want to optimize this one as well. So instead of 0.45, I'm going to put 0.47. Yeah. 1, 2, 3, 4, 5, 6, 7. Good. Now my graph is optimized. As little blank space as possible. That's how we do it whenever we are publishing a graph, publishing a paper with a graph. There's more, right? Let's put the trend line here. Trend line, here you go. Trend line right here. And then we got to put the chart elements as well. Axis title, primary vertical horizontal. That should be T square, and then you put the unit here in between parentheses. This guy is gonna go upstairs. Superscript, right? Bold faced, I wanna make it larger, 16, and okay, italicized to make it look nice. And then we add the other chart element, which is the one along the vertical. 16. 16 here. And this one's gonna be Emma, and then you put the unit in between parentheses, right? So what you're supposed to do now, you're supposed to log the slope, 13117 in my case, the slope 13117. And that's the experiment, the theoretical value of the slope, which is average of P16, okay, the theoretical force, okay? So going back to our equations, right? The slope, that's gonna be my slope. This is the force that I'm taking, but I'm taking the average value divided by 4 pi square r divided 4 pi square r, G16. G16 is this one. Okay, and look at the percentage difference, 2.2. 2.189, right? Almost 2.2. So I want you to plot this graph. Make sure you put the axis title and optimize the graph space as well. I'm going to start calling you to see how you're doing. So step by step, the report plot. Okay, 2. Display regression equation and R square. Okay. Log the slope into cell. Let's see which cell is that. This one right in here, cell H42, last table. In cell H42, last table. Okay. check the percentage difference. If it's a good one or if it is a good one or not. Or not. Okay. Anyone has already finished the plot? Let's see how you're doing. Plot. M versus T square. Superscript, yeah. Jazzy, did you plot your graph already? Molly said she finished. Okay, everything, Molly?
I plotted the graph and I have the equation.
Okay.
And I'm confused because my percent difference is negative 36.4.
36%?
Yeah.
Let me check your group number 2, right? Group number 2, lab 6. Let's see here. I will copy and paste. Let's use this one instead. Make sure you go T square and Emma, right? Group number 2. Yep. And I will insert, and then we have to switch the, yeah, see, sometimes it doesn't allow me. It's so odd, you know? Yeah, sometimes it doesn't allow me to swap there. I do not know why. Oh, now you let me. Okay. And I think I know the reason. You have to click the data points. Okay, so let's take a look here at trend line. Okay, that's what I'm getting here, Molly. Did you get 1.6857 for the slope?
Yes.
Okay, so let's see. 1.6857. Oops. 1.6857. What? What's going on here? Ay. I know that. Okay, number lock. 1.6857. Yeah, we're getting 36%. Don't worry about the negative sign. Why are we getting? We're getting a high value for maybe, well, it's difficult to say, which maybe is this point here that's not good. The extreme here. Okay, that looks like, Molly, the lower point. That looks like it making the, can I do better than that? Wow, that's so odd. Here you go. Yeah, it's not cooperating with me now. Microsoft Word is not cooperating with me. Yeah. Well, but that's okay. You know, you cannot be punished for that because it was the data that I provide to you. Okay. I was trying to see if that was the. Let's see. If she was an outlier or not. I suspect number 1, 2, 3. Let's see. The lowest value is this one here. So it looks like this one is a outlier. This pair of data points. Okay. Let's see.
Okay.
I'm going to eliminate it from the plot. Whoa, what's going on here? Yo. Let's see. Oh, that's because I plugged the wrong one. Okay, this one you got. Insert. Okay. No, I didn't eliminate the right one, did I? Okay. Let's see if we get a better fit now. 0.58. Oh yeah, 0.58. That's because I didn't. I have to invert now. He doesn't let me. Yeah, oh, let's see. It's not highlighting. It's so strange. Sometimes it highlights, sometimes it doesn't. Select data. Edit. Yeah, and he doesn't let me edit either here. Yeah, oh boy, that's so frustrating. Let's see. I gotta do it from scratch. Copy. And paste. Paste the values only. And this one here. Copy and paste. Paste the values only, and I'm going to eliminate this one here. Okay, and let's see how it looks like now. Insert. Three possible ways of doing what I want, right? Oh, wait a minute. What? Ay, 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 ay. Oh, I plot the wrong one. 455. Okay, let's get this one here. Ah, this one here. I'll place it. Here go. Let's see if it goes now. Okay, now we got it. Delete. Okay, now we plot it. Okay, do we get a better value here? 17566. Yeah, we do get, but oh, looks like it's worse. Yeah, it's worse. Okay. Yeah, don't worry. Okay, don't worry about the 35%. Okay, Molly?
Okay, thank you.
Don't worry about. Yeah, instead of getting better, it got worse. So next, Jazzy didn't reply to me, right, Jazzy? Is Jazzy here? Yeah, I'm gonna put a star here under Jazzy. Nuhamin is not here. Liliana is not here. Gabrielle is not here. Molly, okay, Molly plotted the graph. So move on to the next one. Okay, Molly. Now, next, Henry is not here. Laurel, did you plot your graph, Laurel? Working on it? Okay, working on it. Thank you. Ruth's not here. So put the O here. Noemi, did you plot your graph, Noemi? Hello, Noemi. Noemi is not answering. Danae.
I plotted my graph, but I want to make sure that I have my axes correct. If when you press your data, and the purple and blue columns come up, is the blue column the X or Y axis?
Okay, it's written down. Your group, let's see, let me get the same. Your group number?
3.
3, right? Let me get the same spreadsheet that you have.
Okay.
Okay. So do you highlight M and T square, right?
Yeah.
Okay, so let's insert it here. Okay, and you get a graph like that, and you are asking what that you're asking?
That's correct, right? Like with that, my M is on the Y axis, correct?
In this plot that I have right now, the M is in the x-axis.
It's
And
in the X.
yeah,
Okay.
that's right. So you gotta
So
you
when
gotta
I
huh?
so when I switched it though, so for
Uh-huh.
this one, my slope was closest to the theoretical,
Uh-huh.
but when I switched it, it was a lot different.
Okay, so let's see. You're gonna see you shouldn't be close to the theoretical because it's the invert. Okay, add trend line. I didn't invert the graph yet. 1032. Let's see. Yeah, you're right. This
That's what
one.
I got for this one.
Uh-huh.
Yeah.
Let's see. Let's invert and let's see what happens if I invert it. Right?
Okay.
And let's see if I can. Yeah. See, I finally found a way to click and drag. And now let's take a look at the trend line. 9487. Let's see. It's going to be around 29%, 0.9487. Let's see if I have the right equation here. Yeah, I do
Okay.
have the right equation. You're right.
Mhm.
So it's a coincidence, okay? You're getting
So you want me to go with the 0.9487?
yeah, 0.9487, this one. Yeah,
Okay.
because
Just
that's the
making sure.
right one. It was just
Okay.
coincidence that the incorrect graph ended up closer to
Okay.
the goal. Okay?
Okay, thank you.
Okay, so Noemi is working. Noemi, no, the nay, right? The nay. Okay. So let's put working here.
Well, I
Run.
finished all that.
Oh, you already finished? Okay.
Yeah.
Okay, good. Taylor, did you plot your graph?
Yeah.
Okay. Do you have any questions?
No.
Okay. Jeremiah, did you plot a graph? Yes. Okay. Any questions, Jeremiah? No question. Okay. So don't forget, start doing the units, right? Sig figs. And
Oh, Professor, I do have a question.
yeah,
For
just
group 3, how do you said optimize the graph? How
yeah.
do you do
So
that? This
okay.
part.
So let's see. So here you go. You see, you want only this region here in the graph, right? So what do you
Mm-hmm.
do? Let's start with the vertical line. Double click it, and I'm going to do yeah. Double click it, and now you
Uh-huh.
adjust the go to axis option. You adjust the
Yes.
bounds of the axis option. 0.4 here. Let's leave 0.7 for now, and let's see if it's a good one. Okay.
4.7.
Okay, we can do better than that. Let's put 0.45. Let's see. See, I am optimizing the vertical direction, right? Now
Okay.
let's optimize the horizontal direction. Double click here. I want to start with 0.3 all the way up to 0.5. Okay. I can do better with 0.35. Okay. Oh, no, I cannot do better with 0.35. 1, 2, 3, 4, 5, 6, 7. Okay, let's see. Can I do better than that? Let's try 0.34. Yeah, 0.34. Yeah, it worked, right? 0.34
Yeah.
worked.
Okay.
So gotta be a little bit of trial and error until you see the. But don't let one of those points disappear for the graph, right?
Gotcha.
Okay. So that's the one. Next, see here. We were talking to Jeremiah. Sean, did you get the? Did you get your plot? Yes. Okay. Any questions, Sean? No. Are you getting a good percentage difference? What the percentage difference you're getting, Sean? Let's put it here. I'll have to check that, yeah. Log slope, let's put here log slope, right? That will be the next step. Plot it and then log slope and then percentage difference. Like that. Okay, I have to check that. Okay. Okay, so let's go for the next one. I'll get back to you, okay, Sean? Jason straight. Did you plot your graph?
Yes, I did.
Okay, what slope did you get?
I got 0.817.
And what's the percentage difference?
That's the third one in the values, right?
In the, let's see, the cell, I think right in here. Yeah, third one from the bottom to the top, right?
Yeah,
That's why I
the
put
last
it.
one.
Yeah.
Okay, I got 32.0809.
Okay, did you invert the axis of the graph?
I haven't. Hold on, let me see if that works.
Make sure that you invert the axis of the graph, right? And I'm talking to Jason straight. That's number 5. Let's see here. 5. Here you go. T square M. Insert chart. Whoa, that's now let's see. I'm going to swap. Okay, now let's see what's going to be the R square and the slope. Okay, so your slope is not right, okay, Jason? It looks like you didn't invert the graph. You didn't invert it, okay? I'm getting
Yeah,
one.
I did it the other way. My bad.
Yeah.
I'll fix that right now.
Yeah, okay, so. And like I said, there is a very simple way of inverting, right? You click one of the data points, everything is highlighted. Only when everything is highlighted that you manage to swap, right? One column for the other. If you click just the graph, nothing is highlighted. Okay, but when it's highlighted, then Microsoft Word lets you swap. Okay, so that's the little secret. Elena Trujillo.
So for the slope, I got 1.12.
1.12, just like me, right?
Mm-hmm.
And what's the percentage difference you're getting?
I got 6.8918.
Okay, that's a good value. Okay, so you can do the rest now. We have another 6 minutes to go. Jason Valadares. Did you plot your graph?
Yeah.
Okay. Did you log the slope?
Yes, I did.
And what's the percentage difference you got?
Oh, actually, no, I haven't inverted it yet. No, I'm sorry.
Oh,
I'm
you
still
got
working.
inverted. Okay, so I'm gonna put it working on that, okay? Okay, so Audrey, are you there? I got a new computer, so I'm figuring things out. Okay, so let's put working it out, okay? Group number 6, Brianna, are you there, Brianna? Brianna left, right? Yeah. She's not even here. Okay. Now let's put O here. Ali is standard. Ali is not here. And Alia. For T20, one of my values is 1252. Should I change it? Let's see. Let me check here, Molly. Group number 2. 1252 is the first one, right? Okay, so you have two decimal places, right? You have a resolution of 0.01 in the timer. So you have to display two decimal places there in your data. Here you go. Number 1, 2. That's how it's supposed to look like. Okay, Molly? And the same for everything else, right? Two decimal places. 11:56. You're running out of time. Jazzy, is Jazzy? Okay. Hi, Jazzy, are you there? Jazzy is present, but it's not answering. I'm gonna switch it from attendance to star here for Jazzy. Okay. And Molly, let's see. L'Oreal, did you manage to plot the graph? L'Oreal was working on the graph before, trying to invert it. Okay. Okay, if you have too much trouble, you should just do that third option, right? And well, so everything else you can do there at home, right? This, I'm having some computer problem. Oh, Jazzy. Okay. Okay, Jazzy, make sure you have a reliable computer, okay? For those activities, I'm going to put it here. I'm gonna put you're working on that. And anybody else? Nuhamin is no longer here, so I'm gonna say that she's no longer here. Ruth left as well. Brianna Carrillo. Brianna is not here. Was at the beginning, but then she left. Alia Zavala. Ali is here. Are you there, Alia? He's not answering. Okay, I'm gonna put a star here in Alia. And okay, you can stop here. This lab report is going to be due next week. Let me give you the exact date. Report of this lab is due, okay, 11/20th. Oops. 11/20th, 24, right? Which is next week. And I see you next Monday. And have a nice weekend.
Thank you.
Welcome.
Thank you.
Welcome.
Professor, I have a question.
Yes.
So I'm trying to like swap the values for the X and Y axis, and I'm trying to do it the way you were showing me, like you just drag it to the side.
Yeah.
But for some reason, the purple one for M doesn't move at all. Like it only can move up and down, excuse me.
Really?
And then
Okay,
for T, it can move side to side, but then it stops right next to M.
Okay, so can you share your screen with me so I can see if there is any
Yes, I can. One moment.
thing that I can help you with? And this thing varies from computer to computer. It's a shame that Microsoft hasn't fixed that.
Okay, can you see my screen?
Yeah, I can see, but you have to click one of the data points. Make sure you click one of the data points.
Oh, it has to be data point,
Oh,
I think.
yeah.
I
Now
think that
you
was
can.
what.
Yeah, see
I
that?
see. That's
You
what I was
gotta
doing
make
wrong.
sure that the data points are clicked. Otherwise, you
Okay.
won't be able to swap.
And now, okay, I think I need to fix
Now the
my
data points are
axes
outside
now.
the plot. Now the data points are outside
Okay.
the plot. Okay.
Okay. That was it. That was all
Well,
I needed.
do you believe that I discovered that today? I always have this problem, and today, just right now, when I was teaching you, I figured out that that's how we fix it.
I see. Thank you very much, Professor.
Okay.
Have a good day.
You
Bye-bye.
too.
Professor,
Yeah.